Computer graphics simulators were originally designed to be computationally efficient and only visually plausible, so as to be integrated in entertainment content production. Having become more and more accurate over the years, they are now widely used in industrial design to build real-world structures and as part of critical training software in fields such as soft robotics, architecture, and biomedicine. In these domains, the accuracy of the predictions made by the simulators are critical, and so the need for validated simulators is increasingly important. Therefore, in this paper we evaluate the physical realism of computer graphics simulators of slender structures by using measurement protocols from the soft matter physics community. The first protocol we introduce is the cantilever test. In this protocol, a horizontally clamped elastic rod or plate sags under gravity. The sagging deflection is dependent on the material properties of the object, such as bending stiffness, length, and mass. The deformed configuration can be completely defined by the scaling dimensionless parameter gamma that measures the weight against the resistance to bending. The aspect ratio of the sagging object is a universal function of gamma irrespective of the material parameters. Thus, using gamma, we can systematically sample a large set of parameter combinations. We extensively confirm this result in our experiments with fabricated rods and ribbons. Using the dimensionless parameter gamma, we are able to evaluate simulators in a unified way. Despite the simplicity of the test, some simulators do not perform well. Furthermore, for gamma regimes larger than 1000, simulators require an increase in spatial resolution due to the concentration of curvature close to the clamp. We test several rod, ribbon, and plate simulators on this protocol to measure the predictability of the bending model in 1D. While most simulators pass the test, ArcSim and Projective Dynamics do not clear it. We investigate these failure cases further in the paper. The second protocol we introduce is the bend-twist test for curly rods. We present the work of Miller et al. As a measurement protocol to study the coupling between bending and twisting in curly rods. As opposed to the cantilever test, we need a second dimensionless parameter phi to properly categorize the system. Phi by 2 pi determines the number of turns the rod makes. Miller et al. Have shown that as a function of these two dimensionless parameters, the rod might adopt a 2D or 3D equilibrium shape. Again, we compare the theoretical curve against our experiment. Our experimental data indeed confirms the phenomena. This figure shows a superposition of our experimental data along with that of Miller et al. In this test, we set an initial shape with natural curvature and we let the curly rod sag under its own weight. As seen here, depending on the position in the parameter space, each simulation results in a deformed configuration that is either 2D or 3D. This test is quite demanding and passing it requires using enough resolution. In particular, nodal models may have to use a large number of nodes to account for the complex curly geometry of the rod. With sufficient elements and for dynamic models having sufficient time to stabilize to a stable equilibrium configuration, the three rod models from graphics nicely succeed. In contrast, Bacchus has a hard time performing the test, especially near the frontier and for very long and curly rods. The third protocol we introduce is the lateral buckling test, dedicated to ribbons and plates. Unlike the cantilever test, here the plate is clamped vertically. This position might be stable or an unstable one, leading the plate to buckle. At a given Poisson ratio, the stability of this position depends on two dimensionless parameters, gamma and the ratio of width to length. As in the previous experiment, we can observe a clear bifurcation. The vertical configuration goes from stable to an unstable one and crosses a master curve that we have derived. This can be seen here for each simulation as we increase the value of gamma. As this test is an extension to the cantilever test, we only evaluate plate models that were successful on cantilever. Phoenix perfectly passes the test, and all the variants of libshell eventually succeed provided a sufficient mesh resolution is used. In contrast, discrete shell converges to a shifted solution, while Abaqus's Newton method does not prove robust enough to follow our protocol correctly. Lastly, we introduce the stick-slip test as a protocol to measure static friction solvers. This protocol measures the accuracy of simulating static Coulomb friction, and the setup involves a vertically suspended thin elastic rod or ribbon in contact with a substrate. Sanu et al. Have shown that with normal and tangential forces P and Q at the point of contact, that dimensionless quantity Q by P does not depend on the material properties of the object in contact. This ratio thus provides a way to detect the bifurcation between the stick and slip behavior of the elastic object. We confirm this bifurcation boundary through our experiments. Here we see an example of correct simulation behavior depicting the difference between slippage thresholds for friction coefficients 0.1 and 0.3. Convergence to the correct solution on this test requires properly calibrating solver tolerance and simulation time step, as well as ensuring quasi-static behavior. We present our results from the tested friction solvers. Both Sobogus and Abaqus passed the test. Sobogus is tested both coupled to a rod model with superhelix in 2D and to a plate model with ArcSim within the Argus code. On the other hand, the explicit solvers fail to capture the correct threshold and generate excessive sticking.